today's problem is the cross section of beam is as shown in figure. Okay. So this is the cross section of beam. Okay. The beam is hollow with dimensions total width 100 and depth 150. Okay. The question says determine maximum tensile and compressive stresses when beam is subjected to UDL of 2 kilonewton per meter and length of span is 3 meter for first is cantilever beam and second one is the simply supported beam. Okay. So if you plot the bending stress distribution diagram, assuming that this is the location of neutral axis from the base, that is y bar. Okay, so we'll compare the two bending stress distribution diagrams, that is for cantilever beam as well as for simply supported beam. Okay, so we all very well know that the cantilever beam is a beam which is fixed at one end and free at other end. Okay, a UDL is acting on this beam and its length is 3 meters. Okay, so due to the intensity of this UDL, the UDL intensity is 2 kilonewton per meter. The beam is going to deflect, or it is going to bend downwards in clockwise direction. Okay, so if we consider the stresses induced in this beam, the top fiber of the beam, okay, this top fiber will be subjected to tensile stress and the bottom fiber will be subjected to compressive stress. Okay, so let us denote it by first condition, which is for cantilever beam. So if you plot the bending stress distribution diagram, the top portion of the beam, that is this cross section, the top fiber, it will be subjected to tensile stress and not compressive stress. Okay, and the bottom fiber will be subjected to compressive stress. Okay, and similarly the location of neutral axis from the base will be the distance of the extreme fiber which is subjected to compressive stress from neutral axis, that is YC. Because in the conventional cases till now we have seen that due to the transverse loading from the top was subjected to compressive stress and the bottom was subjected to tensile stress. But in cantilever beam it is exactly opposite. The top fiber or the top layer is subjected to tensile stress and the bottom layer is subjected to compressive stress. Okay, so in this case y bar is going to be equal to YC. Okay, and let us consider now second case, simply supported beam. So this was for cantilever beam. In a simply supported beam, the UDL, since it acts about the entire beam span of length 3 meters, okay, 2 kilonewton per meter, so its resolved component will be acting in downward direction and this will force the beam to deflect in downward direction. Okay, and due to which the top portion of this beam, okay, that is this portion, will be subjected to compressive stress and the bottom portion or the bottom fiber, okay, will be subjected to tensile stress. So if we plot the diagram for the simply supported beam, so this will be exactly opposite to that of the cantilever beam. It is the bottom will be subjected to tensile stress, top will be subjected to compressive stress, and the distance of the top layer from the neutral axis will be YC. Distance of bottom layer, extreme layer at bottom from the neutral axis will be equal to YT. Okay, and in this case Y bar, that is location of neutral axis, will be equal to YT. Okay, so please keep in mind the considerations for the cantilever beam as well as for the simply supported. Okay, so as usual, now let us start with the calculation. So first we'll determine the location of neutral axis. Okay, neutral axis, that is Y bar, which is calculated by using the relation summation of AY upon summation of A. Okay, now let us consider the cross section again. So the cross section, since it is a hollow one, so it will be obtained by subtracting the inner cross section from the outer cross section. Okay, so Y bar will be determined by the relation A1 Y1 minus A2 Y2 upon A1 minus A2. Okay, so this is our A1 cross section, and its depth is, total depth is 150. So its centroidal axis will exactly lie about the midspan, that is Y1 will be equal to 75. So if we write down by our usual notation, that is section, then location of the centroidal axis, area, and the product of area into the centroidal axis. So for section 1, y is at distance, y1 is equal to 75, that is half of the total depth. Okay, so y1 is equal to 75 millimeters. Okay, area is, okay, so this is 25, 100 by 150, 100 by 150, a1 y1, sorry, a1 y1 is equal to 100 into 150 into 75. Okay, now consider subsection 2. This one is 2, this is 1. So its dimensions are 75 by 50, and its location from the bottom fiber or the reference edge will be, this centroidal axis will be at 37.5 and plus 50, that is 87.5. So y2, okay, y2 will be at distance 50 plus 37.5. Okay, so I'll write over here y2 is equal to 50 plus 37.5. Okay, so that is y2 is equal to 87.5 millimeters. Okay, the cross sectional area is 75 multiplied by 50. Okay, and the product a2 y2 will be equal to 75 multiplied by 50 multiplied by 87.5. Okay, so let us substitute in the formula to calculate y bar. Is 15000 into 75, that is a1 y1 minus a2 y2. a2 75 into 555 25 35 37 3750 into 87.5 divided by 15000 minus 3750, 15000 minus 3750. Okay, and hence y bar is equal to 70.83 millimeters. Okay, okay, let me check once again. So this is 100 into 150, 100 into 150 into 75. is equal to minus 50 into 75, 87.5 is equal to divided by 100 into 150, 100 into 150 plus 75 into 50, 50 into 75 is equal to, oh, it has to be subtracted. 1500 into 75 equal to minus 3750 into 7.5 is equal to divided by 15000 minus 0. 70.83, yes. So y bar is at a distance of 70.83 from the base. Okay. Then we'll start with the calculation of the moment of inertia, that is Ixx about neutral axis. So this will be simply Ixx1 minus Ixx2. Okay, and the since the two sections, the centroidal axis, they'll not be coincident with the neutral axis. Hence, we'll have to apply the principle of parallel axis. Okay. So this will be BD cube by 12 minus AH square for the first section minus BD cube by 12 minus plus AH square for the second subsection. Okay, so let us substitute the values. Width for the first section is 100 and depth is 150 divided by 12 plus 100 into 150 and h. Okay, so if we consider the total depth, the centroidal axis will be at 75 and y bar is at 70.83. So h is distance between the y bar, that is neutral axis, and the centroidal axis of the section under consideration, is 75 minus 70.83 bracket square. Similarly for, okay, this has to be subtracted. For the second subsection, the cross section is 50 by 75. So 50 into 75 cube divided by 12 plus area 50 into 75 into height. That is the distance between the centroidal axis and the say neutral axis. Okay, so it will be 87.5, the centroidal axis of the second subsection, minus 70.83. 87.5 minus 70.83 bracket square. Okay, so I'm solving this. We'll get the value of the moment of inertia. I is equal to 25.59 into 10 raised to 6 mm raised to 4. Okay. Now let us revise the formula again. M upon I is equal to sigma upon y. Okay, so we have calculated value of I. We know the value of yc as well as yt. Now let us calculate the value of the maximum moment, bending moment for both the beams. That is for simply supported beam and for cantilever beam. Okay, so for simply supported beam carrying a UDL. Okay. So in short, let us revise the concept once again. This is 2 kilonewton per meter running over a span of 3 meters. The shear force diagram will be okay, in this manner, and the bending moment diagram is going to be this way. Okay, this has to be a bit symmetric. Okay. Since the loading is uniform, so exactly the shear force will be zero about the midspan, that is about 1.5 meters from the support. Okay, that is from A, and about 1.5 meter the bending moment is going to be maximum, that is equal to Bm max is equal to WL square by 8. Okay, so I think so we know very well how we have got this value WL square by 8. It is by taking the section about the midspan. So the total length will be L by 2. So the equation will be RA into L by 2. If we consider W as the intensity of the load acting on this beam, so RA will be W by 2, RB will be equal to W by 2. So the equation will be W by 2 into L by 2 minus, again this UDL, it has to be resolved. Its component will be W into L by 2 and it will act at a distance L by 4. So minus W into L by 2 into L by 4. Okay, this will be WL by 2. Okay. So this is going to be WL square by 4 minus WL square by 8. That is equal to 8 WL square minus 4 WL square by 32. That is equal to WL square by 8. Okay. And for a cantilever beam, carrying a UDL, let's say W kilonewton per meter over a span of L meters. Okay, its resolved component will be, okay, this is going to be its free body diagram. That is W into L, and this will act at L by 2. Okay, so the bending moment is surely maximum. Okay, about its fixed end, because if we plot the shear force and bending moment diagram, so for this beam the shear force will be RA will move in upward direction. Okay, and for UDL the shear force diagram is denoted by an inclined line. Okay, and similarly the bending moment diagram will be, this will be the resistive moment acting in anti-clockwise direction, so which will be moving in negative direction, and it has to be connected by using a parabolic path. Okay, so the bending moment about free end is equal to 0. Maximum moment will be induced about the fixed end, that is equal to W into L into L by 2. Okay, Bm max will be equal to W into L by 2, that is equal to WL square by 4. Sorry, WL square by 2. Okay, so let us substitute the values and calculate the maximum bending moment. So W is 2 kilonewton per meter. I'll multiply, okay, I'll keep it as it is in kilonewton per meter, multiplied by L. L will be kept in meters again, that is 3 square divided by 8. So the value of W will be equal to 2 into 9 divided by 8. Into 9 divided by 8, that is 2.255 kilonewton meter. And for a cantilever beam, bending moment max will be equal to 2 into L square, that is 3 square divided by 2. So that will be equal to 2 will get cancelled, 9 kilonewton meter. Okay, first, so we have the value of Mi. Okay. Now we will calculate the value of Yc as well as Yt. Let us go through the diagram once again. For cantilever beam, Y bar will be equal to Yc, hence Y bar is going to be equal to 70.83. Okay. I'll write it down over here. Okay. Y bar is going to be equal to Yc for cantilever beam. Y bar equal to Yc equal to 70.83 mm. Hence Yt will be equal to total depth minus Yc. That is 150 minus 70.83. 70.83. That is equal to 79.17 millimeter. That is the value of Yt for cantilever beam. Okay. And similarly, for simply supported beam, Y bar will be equal to Yt. Y bar is equal to Yt, that is equal to 70.83 millimeters, and Yc will be equal to 150 minus 70.83, that is equal to 79.17 millimeter Yc. Okay, so we have the values with us now. So we will substitute the values to calculate the stress in tensile and compressive stresses in bending. Okay, so for cantilever beam, let us use the relation m upon I equal to sigma upon y. So sigma will be equal to sigma in compression is equal to m upon I into y. So m is equal to 2.25 kilonewton meter. So 2.25 into 10 raised to 6 Newton millimeter. So this will be 2.25 into 10 raised to 6 Newton millimeters divided by I. 25.59 into 10 to power 6 multiplied by Yc. Yc is 79.17 mm. Okay. So sigma c is equal to 6.96 Newton per mm square. 6.96 Newton per mm square. Okay. So again using the relation sigma c upon Yc is equal to sigma t upon yt, hence sigma t will be equal to sigma c upon yc into yt, that is equal to 6.96 divided by yc, 79.17 multiplied by 70.83, hence sigma t is equal to 6.23 Newton per mm square. Okay. And for cantilever beam, again sigma c is equal to m upon I into y. Now only the values of y are going to change. Okay? Because the maximum bending moment, okay, that will also be different. So maximum bending moment in these cases 9 kilonewton meter, that is 9 into 10 raised to 6 Newton mm, divided by I, that is 25.59 into 10 to power 6 multiplied by Yc. Yc in this case is 70.83. So value of sigma c is equal to 9 divided by 25.5 is 24.91 Newton per mm square. Okay, and substituting in this relation, that is sigma c upon yc is equal to sigma t upon yt. So sigma t is equal to sigma c upon yc into yt, that is equal to 24.91 divided by 70.83 multiplied by 79.17. Hence the value of sigma t will be equal to 27.84 Newton per mm square. Okay. Now let us plot the distribution diagrams. So I'll plot them over here itself. So this is the given section. is the location of neutral axis for cantilever beam. Sigma t is at top. Sigma t is equal to 6.23 MPa and sigma c is equal to 6.96. This is yc and yt. Okay, and for simply supported beam, the top will be subjected to compressive stress that is equal to 24.91 megapascal. The bottom will be subjected to tensile stress, that is 27.94. Sigma t is equal to 27.94. Okay, and this is the location of yt and this is the location of yc. Okay, so let us revise again. So we started with the calculation of the neutral axis. Then we moved forth with the calculation of the moment of inertia about the neutral axis. Then we found out the maximum bending moment for the simply supported beam as well as for the cantilever beam, and then we have simply substituted them in the relation m upon I equal to sigma by y to get the respective values of the bending stress. Okay. So this is how the problem is solved.